Welcome to session 5, track 1, and we're going to talk about internationalizing the date-time API consistent with the Earth, the Moon, and leap seconds. Actually, the title I really wanted to have for this talk was Earth, Moon, and Abolishing Leap Seconds, the Curious Astronomy and Politics of the Time Function. But this will be an unusual talk, and I will lead you on a little expedition, a little journey of discovery around some areas that are not usually talked about at the Unicode conference. But first, let me introduce myself. My name is Jim Delahunt. I'm a consultant in solo practice, and I live in Vancouver, Canada. And I want to give you a URL for the slides here. You can go to this URL and download the slides, and the slides have hyperlinks in them which will let you click through to more resources. And the slides will also be up on the conference page in due time. So I'm going to ask a bunch of questions about time and calendars, like how long is a day and how long is a year, and when does a minute have 61 seconds, and how does the Posix time conflict with UTC? It'll be an interesting journey. So let's start off. How long is a day? And in particular, are days longer in summer and shorter in winter? I asked my brother that once, and he said, nah, actually days are always the same length. They always go from sunup to sundown. And I thought that was not a very satisfactory answer, but I wanted fixed length units of time. So here's another model of how long a day is. That it's 24 hours, and there's 60 minutes in each hour and 60 seconds in each minute, adding up to a total of 86,400 seconds exactly per day. But see that bright thing in the picture? Does that have anything to do with how long a day is? Suppose you were to measure from the moment of sunrise on one day to the moment of sunrise of the next day. How long a time would that be? Would that be 86,400 seconds? I suspect not. And would it be the same every day? I suspect not. So there's another way of measuring how long a day is, and it has to do with observing the sun. And that's actually the older way of measuring how long a day is. The kind of theme of this talk is about models and the prototype that the model is based on, that we get from observation. The map is not the territory. The concept of day originates from observing the sun, and that's the fundamental phenomenon. And then this concept of a day being 86,400 seconds of identical length every single day is a model that we've constructed that is based on the observed day as a prototype, but it's not the same as the prototype. And the differences between a model and the prototype it's based on can be wacky, and that's what I'd like to take a little look at. You may be wondering how this idea relates to localization and internationalization and the Unicode conference. Let's think of localization as fitting the product to the reality of what the new market requires. It's going to be language, it's going to be date formats, it's going to be features, it's going to be support and sales. And internationalization is the discipline of coming up with models which make localization easier and cheaper. So we deal with realities and we deal with models in our discipline, but I want us to beware of being blinkered by our models. The human reality that we're working with is complex and it's weird, and we see this in every other presentation about writing systems and about human names, but it's also true about measuring time. And I'll argue that it's our job as internationalists to create new models where necessary, and part of the theme of this talk is, when is it necessary? Well, I promised to talk about the time function, and so let's talk about that a little bit, and also the structure named TM, which holds a time moment in time. This concept appears in lots of programming languages, including Python, including the Unix operating system, and they largely inherited it from the Posix concepts, such as the Posix 1.2008 standard, which in turn inherited from the C standard library concept, which in turn based it on something that Pope Gregory's people came up with 500 years ago in Western Europe. The time function returns a time t type, which is basically an integer, and that is defined to be the time in seconds since the epoch, where the epoch is 00 hours on the 1st of January 1970 in UTC. And there's other related functions like GM time, for example, which takes one of those time t values and returns, as they describe it, a broken down time expressed as UTC, and that's in that structure Tm. Let's take a look at that structure Tm. It's got a number of fields for seconds, minutes, hours, day of the month, month of year, a count of years since 1900, and then day of week, day of year, and a flag for its daylight savings time apply. So file that away in your memory, take a look at those fields, see if there's anything interesting about how they're defined and how they're constrained, and let's carry on and talk about that structure in a little bit more detail. In the Posix standards and various documents that are derived from it, there's a section 4.16, which is seconds since the epoch, and it has some clarification about what the standard means when they say the time function returns the seconds since the epoch. One of the things they say is that the actual time of day related to has an unspecified relationship to the number of seconds since the epoch. So they do not promise that you can call the time function, get back a count of seconds since the epoch, and convert it into a time and have it match the time of day. Maybe that's going to be true, maybe it'll be close but a little bit off, maybe it'll be completely off, but the standard does not promise anything. Another thing that the standard does promise is that each day shall be exactly 86,400 seconds, and they give a formula relating that time number, that time integer, to the various fields of the TM structure of seconds, minutes, hours, days in the year, and year number. And I've pasted that formula in there. The first line of that formula is just turning seconds into hours, minutes, and days. And the next two lines of the formula are all about calculating leap year correctly in terms of seconds, where 86,400 seconds is a day. But the important thing to note there is they have a very fixed idea of a day shall be exactly 86,400 seconds, and they're happy to calculate minutes, hours, and days, and months based on that model. So let's go back to the question of how long is a day. And I want to specifically ask you about the day 1st of November 2020. How long is that day? And in particular, how long is that day going to be in the state of California? It's going to be 25 hours long. Most days are 24 hours long, but 1st of November happens to be the date when California is going to fall back from daylight savings time to Pacific Standard Time. And because the clock is set backwards in the middle of the night, that day, measured from midnight to midnight, will be 25 hours long. What about in the Yukon? It's a bit north of California, and right now it's the same time zone, UTC minus 7 hours. How long will its day be on 1st of November? And the answer is it's going to be 24 hours, not 25 hours. Why is it different? Because Yukon has decided that they are leaving the daylight savings time rat race, or rather, they're going to leave the time change rat race. They're going to stick with their present Pacific Daylight Time zone and call it Yukon Standard Time from here on out. And they'll be at UTC -7 with no daylight savings time change in November. So their day is 24 hours long, and California's day is 25 hours long. How long is a day again? This, of course, points to time zones and daylight savings time as a special case of time zones. And it's important to bear in mind that time zones and daylight savings time changes are human and political constructs, and they make the model much more complex, and they reflect physical reality in the sense that for the time zone is a balance between having the time reflect the sun rising in the morning and being at its highest at about noon and setting in the evening. And they want to adjust local time to make that more or less true, but they also want to have some consistency in times so that different places will have predictable time relationships. And daylight savings time is all about dealing with the fact that there's the sun rises later and sets earlier in the winter, and in order to take advantage of daylight, they shift the idea is to shift the clock by an hour. But all of these are human decisions to bend and adjust a model, a simple, clean model, to take into account the reality of the sun and the seasons and what humans prefer. And also, humans change their mind about these decisions. You've probably heard about the IANA time zone database. It used to be called the Olson database. And it is a project to keep track of all these changes in daylight savings time data and time zone data, and publish a couple times a year a block of data which describes all of the time zones and daylight savings times rules. But boy, those rules change. If you go to this timetimeonline.com site, one of the things they do is they harvest information from the IANA time zone database to count, to show you all the changes that are happening in each year. And this is a plot of how many changes to time zone rules have happened in each of the last 4 years as measured by this website. And the answer is every year something changes. And looking through the lists of changes is interesting. I'm not going to take the time to go through them now, but I encourage you to check it out. People keep on changing their mind about what time they want to be in. So we've been talking about data structures that have to do with seconds and hours, and that's timekeeping. But let's turn our attention to keeping track of days and years. That's calendaring, where we think of calendar as a system of organizing days. And when we think of a calendar, there's two big things that a calendar needs to keep track of, or rather that a calendar is influenced by. And those two things are the sun and the moon. So, in what way? The moon runs through phases, and I call out the new moon, which is when the moon is between the Earth and the sun, and from the Earth it appears to be mostly dark, because that's a useful punctuation mark in the moon's cycle, and it's easy to make out with a fair degree of precision. And the moon goes through its phases from orbiting around the Earth on a cycle that's about 29.5 days long. Now the sun, well, the Earth orbits around the sun, but we can divide that orbit period we can call it a year, and that's about 365.24 days, more or less, and we can pick out milestones along that progression The March equinox is the time when the sun rises pretty much due east and sets pretty much due west, and the daytime is just a shade longer than the nighttime, but they're pretty close to equal, and that's where the term equinox came from. And then the complement to those are the solstices. That's when the sun is highest in the sky or lowest in the sky, and that's 3 months offset from roughly from the March and September equinoxes. And the movement of the Earth around the sun and the sun's effect on the Earth's climate has a huge impact on agriculture, so it has been important in human culture for thousands of years. Just to refresh everybody's memory, this is how the geometry of the Earth going around the sun looks. You see the sun in the middle, and the blue planet is Earth, and the Earth is inclined relative to the plane that it's orbiting in. And you can see that in the solstices, the Earth is at a point in its orbit where one pole is inclined as much towards the sun as it's ever going to get, and the other pole is inclined away from the sun. And at the opposite solstice, that reverses itself. So the December solstice is winter for the Northern Hemisphere, and the June solstice is summer for the Northern Hemisphere. And conversely, the equinox is when the Earth is 90 degrees further around its orbit from the solstice, and the inclination of the Earth is such that neither the North nor the South Pole is tilted towards the sun, that they're equidistant. So that's what's going on in physical reality. And it turns out that using ancient technology, it's possible to identify which day the equinox happens fairly easily. You make a really simple sundial of a flat surface with an upright rod, and during the day, as the sun moves relative to the sundial, the shadow cast by the tip of that rod is going to move across the surface. So every so often, you make a mark where the tip of the shadow is on that surface and connect those dots. And most days of the year, you'll get a curve, but on the equinox, that will be pretty much a straight line. And the following day, the shadow line will be further along the page on the far side of that straight equinox line and starting to curve in the opposite direction. So if you are using this ancient tech and are diligent, you can plot the shadow that's moving across a flat surface and pretty reliably pick out when the equinox happens. Which means that humans have known that the sun's relationship to the Earth changes over a cycle and have been able to identify at least the equinox points of that cycle with good precision for a long time. So from this comes calendars. And I want to run through a number of calendars that I got from reading this interesting article. The archived summary is a link to a web page which reproduces one of the essays from this book, but the book is the source of the knowledge. And it's fascinating the detail they have there, and that's not even the complete story. So and I'm going to run through all these calendars fairly quickly, not to understand each one in detail, because I don't understand them all in detail, but to just observe how much variety there is in the calendars humans have come up with over their cultures and over time. So the first calendar is based on astronomy, on observing the relationship between the Earth and the sun over time and the moon over time. So the tropical year is the astronomy term for a year, a cycle of the Earth around the sun as measured through observations. And the March equinox is an interesting milestone there. It's feasible to measure, and you can use that to tell how long a year is. The synodic month is the name for a month, the moon, the period of moon motion relative to the Earth. And in particular, you can punctuate that with the new moon, which is the point where the moon is between the Earth and the sun, and therefore the Earth is not able to see much of the moon because the side that is close to the Earth is dark. So that's one calendar. There's a Julian calendar, which is named after Julius Caesar. It has 365 or 366 days a year. There are leap years every so often. But it follows that cycle rigidly. And as a result, it loses sync with the solar year. And it did that once in year 45. And so Julius had to reform the calendar and reset some things. And it got out of sync pretty badly by the 1580s. And that's what prompted the next calendar, the Gregorian calendar, which was established to fix the problem of the Julian calendar that Europe was using, having lost sync, and B, to change the rules for which years have 365 days and which have 366 days in order to make it closer to the sun's actual relationship to the Earth. And the Gregorian calendar is famous for having a 400-year cycle where in the course of 400 years there are 97 leap years, mostly every 4 years, but not some of the time and unexpectedly some of the time in part of the 400-year cycle. So that's a calendar. There is a calendar, and I'm now here we're getting to places which I know only from reading Wikipedia, and I would be interested to know if there's somebody in the listening to the talk who knows about this from more personal experience and can correct or elaborate on any of these summaries. The solar Hijri calendar, which is used in Iran and Afghanistan, has 365 or 366 days a year. The year begins on the observed March equinox, and my understanding is that the rule for adding a leap day is you count through 365 days of the year from the previous March equinox, and you look at your sundial, and if the next year's equinox has not yet arrived, you throw in a leap day at the end of the year. And so that means that the leap day arrives every 4 to 5 years on various cycles, which are described as 33-year cycles or 29-year cycles or 37-year cycles. Fairly complicated, but really it comes down to observations and the Earth's motion around the sun and the arrival of the equinox is not predictable. It varies based on the physics of the sun and the Earth moving around the sun. So it is not a simple pattern. Another calendar was actually a predecessor to the solar Hijri is the Jalali calendar, which also has 365 or 366 days a year. But interestingly, the months, the passage from one month to the next and the length of the month is based on observing solar movement relative to constellations in Earth's sky. And months can be from 29 to 31 days long. And the knock against this calendar apparently is that it was complicated to do the observations to tell when you move from one month to the next. But on the other hand, it was really good at staying in sync with the sun because it was based on observation all the time. More calendars. The lunar Hijri calendar, sometimes called the Islamic calendar, is in contrast not based on the sun, it's based on the moon. And months start when people on Earth can observe the new moon and the crescent of light from the new moon. And so it has a cycle of 354 or 355 days a year, which you'll observe is less than 365.24. And that means that the Hijri year shifts through the solar year. And sometimes a particular month of the Hijri calendar will occur during the spring, and sometimes it'll occur during the fall. And that goes over in a 30-year cycle. And in that 30-year cycle, there's 11 leap years. Next, the Hebrew calendar has either 355 or 354 or 353 days, depending on some rules. And they sometimes throw in an extra month of 30 days, which makes the year much longer. It is originally based on a combination of a lunar month and a solar month, but they have since figured out calculations which let them figure out which years have the leap month added in. And there's a 19-year cycle, and in 7 of those years, there's a 13-month thrown in. More calendars. There's a Chinese traditional calendar, which was timed by observation of the moon and sun. Had, interestingly, the same number of days per year as the Hebrew calendar, and the same concept of an extra month thrown in when you need to align with the solar cycle. And there's a 60-year super cycle that this calendar is aligned along. There is an Indian calendar, which since 1957 has been aligned along with the Gregorian calendar, but there's older roots to that. So clearly what we see from this is that the sun and the moon are really important things to humans when making a calendar. And that's a very big difference from a simple model where the day is always 86,400 seconds long and there's a predetermined number of days in the year. So let's shift gears and start talking about time standards, how you build up from seconds to days to years. There is one time standard called TAI, which is the International Atomic Time, and this is kept by atomic clocks, which are counting International System of Units seconds very precisely, and they just count forward without regard to where the sun is, without regard to where the moon is. There is also a calendar called Universal Time, which is based on observations of the sun's position relative to the Earth at 0 degrees west longitude, which is the prime meridian. And those days, because they're based on where the Earth is relative to the sun, are not 86,400 SI seconds long. They will be different lengths of time. There is another time standard called the GPS time standard. Like TAI, it is based on atomic clocks, but it is 19 seconds off of TAI. So this is interesting. This is a chart of UT1's measurement of how long a day is based on solar observation relative to the 86,400 second model of how long a day is. And the 0 millisecond line, where the observed day is exactly 86,400 seconds long, is kind of towards the bottom of the chart, and you will see that the gray observations go up and down in the range of 1 to 4 milliseconds longer than the modeled day. And the green line is a 365-day moving average. The diagonal red line is the cumulative deviation, and the dots, which you are a little bit hard to see on this chart, are where that deviation was corrected by using leap seconds. And we're going to talk about leap seconds in a little bit. And note that this is a chart covering about 45 years of time. So we have UT1, which is based on the sun and solar observations, and we have TAI, which is based on international system seconds of constant duration without regard to the sun. How do you reconcile this? Well, that's where the time standard UTC comes in, Coordinated Universal Time. What this does is it counts the same seconds as TAI, but it aims to keep its time close to UT1's observed times, and the way it does that is by adding in leap seconds from time to time to offset that deviation that was in the previous chart. It's always an integer number of SI seconds behind TAI, and right now that difference is 37 seconds. And I'll just step back and make an observation that we were talking before about the tension between model and reality of the prototype. And UTC shows humans choosing to go with the reality of solar movement and solar observation over the very clean, perfect model, which is TAI. So more about leap seconds. The way they work is that there are certain times in the year when the people in charge can inject leap seconds. And the two times that have been used so far since the system started in early 1970s are the 30th of June of the 31st of December, UTC, and it's the last minute of that day. And so what you will see if they decide to inject a leap second is that that last minute will be 61 seconds long instead of 60 seconds long, and the clock will read 23:59:59 and then 23:59:60, and then it will read 00:00:00. In the 49 years that we've been doing this system, there have been 27 leap seconds, so that's a bit more than 50% of the years. But if you look at the chart of when these happened, there were a bunch in the early years, and there's fewer, or they occur less often now, and I'm not quite sure why that is. So let's go back to our friend the time function. Remember that it said the actual day, time of day is unspecified relative to the seconds since the epoch, and they say that each day shall be exactly 86,400 seconds long. So in other words, with this section 4.16, Posix and standard C are punting the leap second. They are not attempting to incorporate the concept of a leap second and UTC into their model of time. I will give them credit for saying in their TM structure that the seconds field, TM_sec, can go up to 60. So they're making an effort to include it, but they're not fully including it. Part of why this is that time was invented for a particular purpose that involved keeping computer servers synchronized, and it assumed that the clocks these servers would have would be drifting a bit, and so that you could essentially bury a leap second or something like that into the error of the system clocks, and it wouldn't be that big a deal. However, in our modern world, there are some time-critical automated tasks, some to do with computing, some to do with trading and finance, some to do with automation that runs continuously, and these tasks involve increasing time accuracy to the millisecond and nanosecond, and for them, unpredictable leap seconds being injected into the time stream are a problem. And part of the problem is that there is not a really good system for passing advance notice to these automated tasks about when leap seconds will occur. And part of the problem is that in some time zones, for instance Japan, the leap second time occurs during work hours. 23:59:60 sounds like it's in the end of the day and out of the way, but somewhere in the world, that time is right in the middle of peak work hours. And so having this leap second occur where everybody's working and all the systems are up and busy is a problem. So there has been a proposal to abolish leap seconds and have UTC turn into basically a cousin of TAI with just seconds advancing and no allowance for solar behavior, solar observation. It's been debated from 2005 to the present, and it keeps on being a debate of the form arguments traded back and forth, and a plan made that at some big international policymaking conference they're going to take a vote and make a decision about this, and that conference comes and they punt the question off for a few more years to the next conference. But the case for abolishing is that for highly precise time-critical work, leap seconds pose problems, and that the Posix interface does not have good support for leap seconds. The advance notice of leap seconds is not being distributed well enough, and that it would be too confusing to have multiple timescales, so what they want is one timescale that meets their needs. On the other hand, there's a case for retaining leap seconds, and I've got to admit that I have a bit of sympathy towards this. And that says that we should have multiple time scales. If you've got a time critical task, use TAI, don't use UTC. If you need to synchronize precisely, use a better time sync algorithm than network time protocol. Something that is using an algorithm that will be precise to nanoseconds if you need it. And regarding the disruption that a leap second causes, you can make an observation that daylight savings time already introduces a 1 hour long, a 3,600 second long disruption in calendars twice a year. And compared to that, a leap second, which occurs some but not all years, and it's just 1 second long, is much less of a change. And finally, if there were no leap seconds, then the calendar would drift out of sync with the solar year. And summer, instead of being in August, would move to a different part of the year. And I expect that people would find that disorienting. There's a really nice essay by someone named Steve Allen. It's a web page with a bunch of commentary and a bunch of links, actually, called Plots of the Time Dilemma. And he makes an observation. You can get 3 goals for a time system. You can have a precise time, or another way to think of it is a stable, precise frequency for measuring events. You can have simplicity, and you can have connection to solar days and solar years. Pick any 2 of those. You don't get all 3. And Steve Allen's observation is that advocates on various sides of the abolition of leap seconds debate have picked their own 2 out of the 3 goals and completely disregard the 3rd goal and the value of the 3rd goal. And he asks the question, which I agree with, why not have multiple time scales? That's the clear answer to this problem. So let's bring this conversation back around to localization and internationalization. I'll repeat what I said before. Localization is about dealing with the reality of a new market and what you need to do to the product to make it fit that new market. Internationalization is about coming up with models and abstractions which make localization easier and cheaper. And one thing you see all through this conference is that human reality is complex and weird. And that applies to writing systems and to names and also to timekeeping. And I also believe that humans cannot resist the solar day and the solar year. So if you agree with the analysis that you can have goals of precise or simple or solar connected and pick any 2, humans are going to want to have solar connection. But as people who deal in internationalization and localization, beware of being blinkered by your models, by your 86,400 second year. The models are helpful, but they are an approximation. Reality is more complicated and more weird. Be ready to recognize when it's time to create a new model to better deal with the complex reality, and be ready to advocate for reality over the model when they conflict. So that's my meditation on the Earth, the Moon, and time. I'm happy to have Q&A now. We should have a few minutes available for that. Here again is the URL for the slides, and I will look forward to hearing and answering questions. Thank you very much.